Hi everyone, welcome to the lecture series of Unit 1 in Linear Integrated Circuits. In this video, we are going to discuss about the voltage controlled oscillator VCO. It is the oscillator whose frequency can be controlled by the external voltage. In this oscillator, the frequency of is controlled by the external voltage, where it can be used for frequency modulation or phase modulation by applying a modulating signal to control input. We are controlling the input by applying a modulating signal, where VCO is also an integral part of a phase loop lock, where phase loop lock is simply said to be PLL. It is one of the important topic in the Unit 3, where the common type of VCO available in IC form is Signetics NE bar SE566. It is a 8-pin IC where first pin is ground and second pin has no connection, third pin has square wave output and fourth pin has triangular wave output, where fifth pin has modulating input. The modulating input is given to the fifth pin of this IC, and sixth pin is RT. RT is a timing resistor, and CT is applied to the seventh pin. CT is the timing capacitance, and plus VCC is applied to the eighth pin of this IC. This is the circuit diagram of VCO, where this contains a constant current source or sink and buffer and a schematic trigger and one inverter, where CT and RT is connected is 6th and 7th pin, and it is a buffer, and RA and RB are resistor which is connected to the current source or current sink. Plus VC is applied to the 8th pin of this IC, where this buffer produces a triangular waveform and this inverter produces a square waveform which inverts the schematic trigger output and produces its output as a square waveform, where this buffer acts as a temporary storage device and this inverter inverts the output of this schematic trigger. This where the schematic trigger output is like this. It starts from positive to high to low, where it inverts the inverter inverts this output as, and it gives the output as low to high. Okay, as I said earlier, CT is a timing capacitor and RT is a timing resistor. The working of the VCO is as follows. The CT is linearly charged. This CT timing capacitance is linearly charged or discharged by a constant current source. This CT is linearly charged or discharged by this constant current source. So the amount of current can be controlled by changing the voltage VCC. By changing this voltage VCC, the current can be controlled and applied to the modulating input. This current can be controlled and applied to the modulating input, or by changing the timing resistor external to the IC chip, or by the changing this timing resistance to which is placed in the external to this IC chip, where pin 5 and pin 6 has same voltage. This pin 5 and pin 6 has same voltage. Thus, the modulating input voltage at pin 5 is increased. The voltage at pin 6 also increases, which results in voltage across RT and thereby decreases in the change in current also. So, where it results in less voltage across RT and thereby decreasing the charging current also. The voltage across this CT is exceeds at 0.5 VCC during charging. Okay, so the output of this schematic trigger. So the output of this schematic trigger goes low at this 0.5 VCC. When it is at 0.25 VCC, the capacitor discharges. Okay, at 0.25 VCC, the capacitance CT is discharging. When at 0.5, the capacitance CT is at charging. So the output of the schematic trigger goes high. When the capacitor is discharging, the output of the schematic trigger is high. When the capacitor is charging, the output of the schematic trigger is low. So which gives the triangular voltage waveform across CT, where this process gives a triangular voltage waveform across this CT, which is also available in this pin 4 as a triangular waveform. As I said, the square wave of the schematic trigger is inverted by this inverter by A3. This inverter is named as A3 and it is also available at pin 3. This inverter output is also available at pin 3 as a square waveform. Inverter is basically a current amplifier used to drive the load. This inverter is basically used as a current amplifier which is used to drive the load. Okay. These are the output frequencies which is appeared in the fourth and third pin of this IC. The fourth pin produces a triangular waveform and the third pin produces a square waveform, where this triangular waveform is high when the 0.5 VCC is applied, where at 0.25 VCC the triangular waveform is at low. This is the output of pin 4. Okay, so the schematic trigger output is by applying VCC, 0.5 VCC, the schematic trigger output is low. At 0.25 VCC, the schematic trigger output is high, where the inverter inverts this output of from square schematic trigger and produces this output square waveform. Okay, where the total voltage on capacitor changes from 0.525 VCC to 0.5 VCC. The capacitance CT is a capacitance. The total voltage on that capacitance varies from 0.25 VCC to 0.5 VCC. Thus, the del V is equal to 0.25 VCC. Then del V by del T is equal to I by CT, where del V is a change in voltage and del T is a change in time, is equal to I. I is a current flows through this circuit, then by CT. CT is a timing capacitance. So by substituting the del V value is 0.25 VCC and we have to find out the del T. So del T is equal to 0.25 VCC into CT divided by I. Okay, where capital T is equal to 2 del T, where capital T is time period. So we have to find F naught. F naught is equal to 1 by T. F is equal to, we already know about F, frequency is equal to 1 by T, where F naught is equal to here 1 by T, where 1 by 2, substituting the capital T value, it becomes 1 by 2 del T is equal to 1 divided by, we are substituting here del T value. So 2 into 0.25 into CT, VCC CT divided by I, where 2 into 0.25 is 0.5. This I goes up. Okay, this I goes to the numerator. But I is calculated by using this method VCC minus VC by RT, where it becomes from the circuit this VCC minus this VC divided by this RT. So it becomes like this. So F naught is equal to VCC minus, by substituting this I value, it becomes F naught becomes VCC minus VC divided by RT, the whole divided by 0.5 VCC CT. Then this RT goes to the denominator, then it becomes 1 divided by 2. 1 divided by 0.5 is 2. Okay, then 2 into VCC minus VC divided by CT RT into VC. So F naught becomes 2 into VCC minus 7 by 8 VCC. Condition of with no modulation input signal. Okay, so this VCC becomes like this. So by substituting, by taking LCM here, we got 2 into 8 VCC. 8 VCC minus 7 VCC by 8. Okay, then this 2 and this 8 get cancelled, then this equation becomes 8 VCC minus 7 VCC by 4 divided by CT RT into VCC. Then next this 4 goes to denominator, then VCC divided by 4 CT RT VCC. So 8 VCC minus 7 VCC becomes plus 1 VCC. Okay, so by getting cancelled, VCC and this VCC get cancelled, Then 1 divided by 4 is 0.25. Then CT/RT becomes, so F naught frequency becomes 0.25 divided by RT into CT. These are the calculations for the voltage controlled oscillator.